Hello, stats class. Here's lesson 5.1b, which is about simulations. Make sure you spell it right. It's not stimulations, it's simulations. And we're going to learn how to do experimental probability in a big way. It's basically about using chance to imitate a real life situation. And what this is usually used for is if it's hard to calculate the theoretical probability, you might do an experimental probability to estimate it. And what you want to do is set it up so it has the same probabilities as in the real situation. And I'm going to give you 3 examples of this today. Because it's so important that you know the general idea. I'm going to use the 4-step process, which we've seen before, to talk about how to do a good simulation. And as I go on this first one, I'll give you the details of the 4-step process along with an example, and then I'll do a few more examples after that. So this first example is probably the most important one. Step 1, as you know, is state the question you want to answer. And usually that's a question about the probability of something in a real life situation. We saw one of these in the warm-up, and I'll use that as my example for this first one. For example, in the warm-up, we asked, how likely is it for 3 friends out of 7 to win the prize, given that the probability of an individual win is 1/6. And it seemed pretty unlikely, and we experimented with that in the warm-up, and we'll use that as our example. So that's the stating of the question. Step 2 is plan. And the plan has to involve how are we going to simulate this situation, or how are we going to imitate it with chance. And this was given to you in the warm-up, but in general, there's a lot of options here. We have physical methods. So not just talking about the 1/6 chance, but in general, you could use dice. Dice worked well for the 1/6, but it wouldn't always. It works well for anything that's 1 chance in 6 or something like that. Coin flips are a physical method. You could do a spinner. You could draw things out of a hat. You could shuffle cards and deal them, etc., etc. And then there's also more abstract methods that are more in your brain and less physical hands-on. And abstract methods include the randint function on your calculator. I believe there's a random.com or something like that that you should look up and see what they have as options. There's table D, which is the random digit table. Those are the 2 most common, is technology or random digit tables. So in my example of the 1 in 6 wins, we could roll a die, and some of you did that in the warm-up, and others chose the technological method, and that's fine. So, but I could choose to roll a die, and I could decide in advance. The planning stage is when you decide what represents what. So I might decide in advance that 1 through 5 are losing rolls, and 6 is a winning roll. And 1 trial, I have to decide how big 1 trial is because there were 7 friends in this real situation. I would say 1 trial is 7 rolls of my die. And I'm going to count what? I'm going to think about what is it I want to know. I want to know probability of 3 out of 7. So I'm going to count how many winners. or 6s, whichever way you want to look at it. Or in other words, I'm deciding what it is I'm going to record for each trial. And then I'm going to repeat that many times. That part is always a step in the plan. I'm going to repeat it many times, and I'm going to find the probability of what it is I'm trying to answer, the probability of getting 3 or more out of 7. And you did that in the warm-up, so I kind of guided you through the plan already in the warm-up, but all of that should be part of your plan. What are you going to do? How are you going to make the probabilities match? How many times is a trial? What are you going to record for your trial? All of this is important parts of the plan. And I would say maybe the plan is the hardest part. Sometimes I'll do the plan for you, or the book will do the plan for you, and other times they're going to ask you to write the plan, and that's a little bit more challenging. Step 3 is the do. Obviously, you would carry out your plan. Many times. Fill out the results. The calculations could either be in the do or in the conclude. I'm going to put them in the do. Calculate a probability, because that's part of what you need to do. And then you use that for step 4, which is conclude, where you answer the question. You use that probability that you calculated. Basically, we are trying to decide how likely is it, and is it unusual? So we're trying to decide if the actual result that happened in the real life situation is unusual or not. Because if it's unusual, then we have something suspicious going on that we might want to investigate further. And that unusual thing, the most common cutoff for that is 5%. So I'm going to put that on here, and we're going to see a lot of that in the next several chapters. It's going to keep coming back. Less than 5% probability is considered unusual. We'll talk some more later about why that is the most common cutoff. It's considered unusual, which is also called significant, and you've heard that word before. Statistically significant would be so unlikely that it's less than 5%, and that's not the only possible cutoff point, but it's the most common. So that's the general 4 steps. And then I'm going to do 2 more examples and just mostly talk about the plan stage and the state, and not do the do, because doing is easy once you have a plan. I'd say the hardest part is writing the plan. So I'm going to do 2 more examples of writing a plan just to get you the general idea of that. So here's another example. Let's say there are prizes available in cereal boxes. There's 5 prizes, and the company says they're equally likely, which we're going to trust them on that for now. And this time, instead of seeing how many of a certain prize I get or anything, I'm going to change it a little bit and say, I'm going to say I want to collect all 5 prizes. So my goal is to keep trying until I have all 5 prizes. That's the real life situation. And I'm asking myself, how many times am I going to have to keep trying? You know, I wonder if I have to buy 10 cereal boxes to get all 5. I mean, if I'm really lucky, I'll buy 5 cereal boxes and I'll get all 5 prizes already, but that seems unlikely to me. So let's do the state as I want to know the probability that I will need to buy more than 10 boxes before I get all the prizes. So I made that state really short. I didn't write it as a complete sentence, but I could have. I wrote it in probability symbols instead. I want to know the probability of this happening. And if you'd rather write it in a sentence, that is fine. the plan. Okay, so I need to set up a situation where there are 5 equally likely outcomes. So I could do that with cards in a hat that I'm drawing. I'm going to do it 2 ways and number them 1 through 5. And I would need to draw them one at a time, but I don't want to put them back after I draw them, right? So draw without or with replacement. I want to put them back after I draw each one. And I'm going to keep drawing with replacement and mixing them in between until I get all 5 and record how many times it took. And repeat many times and calculate the probability. So that's one way that I could do it. Or I could do it with random digits, and I could say something like rand_int on my calculator, numbers from 1 to 5, and I need 10 of them at a time. And it wouldn't matter if I had duplicates, right? Because I might get duplicate prizes. So then I would record whether all 5 appear in that group. And so I'm recording yeses and nos. Or if I prefer, I could just keep repeating until all 5 appear and record how many boxes it took. And I have some choices here. If all I care about is whether it's more than 10 or not, then maybe I don't need to see how many boxes it took. I just record whether I succeeded in 10 boxes or not. Or I might care how many it was, and so repeat until all 5 appear and record how many it took. How many simulated boxes it took. So there's a couple of different options here. And there's no right or wrong way to do the plan, except that you have to make it match the probabilities. So if you don't have 5 equally likely things, then we're in trouble. If you're doing it with a random digit table, I probably won't write this one down, but I'll just say it. You could decide that rather than throwing out the 9s and 7s and any number bigger than 5, you could say, okay, 0 and 1 represent the first prize and 2 and 3 represent the second prize. And as long as you're clear about that and they're equally likely like it says, that is also correct. So if you're using the random digit table, you might want to come up with a way to not have to throw out those extra numbers. And then here's one more example just to be sure, because I feel like the more examples you see, the better. Here's a small high school, obviously 95 students. That's not, well, no, it's not 95 students in the whole school, but 95 students who have parking permits. And let's say this particular school has some VIP spots where two people per week, 2 per week are drawn randomly to get the VIP spots. Ooh, for this week, I get to park in the VIP spot. I'm so excited. Very important person. And one particular week, both of them happened to go to AP Stat students, and somebody got suspicious about that. I wonder how likely that is. Ooh, maybe they're cheating because they were the ones drawing the names or something. AP Stats class has 19 students in it. How likely is that? That's my state. That both winners in the same week are from AP Stats. If it's not rigged. So we're going to assume that those 95 students all were equally likely to be chosen, and it's not being rigged. All right, so I need to represent my 95 students somehow. I could put 95 numbers on pieces of paper and draw them out of a hat, or let's use Table D this time just for a good example of that. Table D, I would number my students 01 through 95 that represent my 95 students. And I would be throwing out anything else. 96 through 99 and 00. If I happen to get those, I'll throw them out. Let's let AP Stat students be the first 19. 01 through 19, and everybody else is not AP Stats. So that represents everyone else. So what I'm doing first is deciding how to make the probabilities match the real life situation. I have 95 students. I have 19 of them that are AP Stats and the rest are not. And then what am I going to do with this? I'm going to take 2 digits at a time off the table, of course. I'm going to take 2 groups of 2 to count as the winners. 1 trial equals 2 groups of 2. Winners. And I'm going to record whether those winners are both from AP Stats or not. Or maybe I'll just record how many AP Stats students are in the pair. I would need to throw out duplicates if there were any, so somebody can't win twice in the same week. It's always important to think about whether you would need to throw out duplicates. I didn't need to throw out duplicates on the cereal boxes because I might get the same prize in 2 different boxes, and that's fine. But I would throw out duplicates here. I would repeat many times, plot the results, which are the recorded numbers of how many in each, and I'd want to find the probability that 2 out of 2 are AP Stats. Okay, so that's some examples of planning a simulation. And like I said, is probably the hardest part. Doing the plan is not so bad if the plan is well written. So you'll be doing some planning in your homework, and there's your examples. That's it for 5.1b.